Today I'm going to talk about VABO, violation-aware Bayesian optimization for closed-loop control performance optimization with unmodeled constraints. So this is a joint work with my advisors from EPFL and EMPA, and our colleagues from Mitsubishi Electric Research Laboratories. So controllers are designed with specific objective. We can tune the internal variables of the control system to optimize the closed-loop performance. For example, in a building, we want to minimize the energy consumption. In an airborne wind energy system, we try to maximize the power production. In the vapor compression system, we try to minimize the steady-state power. So the conventional approach to solving this problem is closed-loop model identification. But the challenge is that it can be expensive and complicated to do the model identification. For example, an industrial vapor compression system model has more than 10,000 equations. What makes this problem even more challenging is the presence of unmodeled constraints. For example, in the building, we try to keep the room temperature in comfort range. In the airborne wind energy system, we try to avoid collision. In the vapor compression system, we try to keep the discharge temperature below a threshold. So here, the common challenge is it's hard to explicitly model the mapping from the internal variables of the system to the performance or constraint functions. And we are also facing the efficiency challenge. For example, in the building, we typically only get one sample per day. And in the airborne wind energy system, it can be expensive to move the airborne. And in the vapor compression system, it typically takes more than 10 minutes simulation time to just get one sample. So how can we solve this problem? Before I introduce our solution, let us first abstract the problem. So we consider a dynamical system. And on top of that dynamical system, we have a controller kappa, parameterized by theta. For example, PID controller or model predictive controller that takes observations Y from the system and applies control U to it. As I've told you, in many of the applications, the system is just a black box to us. For example, it could be a real-world building system, or it could be a complicated software that has thousands of lines of code. So conventionally, how to solve this problem? We can hire a bunch of experts that, based on their experience, choose some parameter theta to run the system, either by hardware or software simulation. And then we can collect the trajectory of control and observation and calculate the objective L and the constant G. And our objective to minimize the cost L subject to that G is not positive. But the problem with this approach is that it can take lots of human effort. So the question is, can we take humans out of the loop? The answer is yes. Recently, as a type of efficient global optimization method, Bayesian optimization is getting more and more popular to solve such closed-loop optimization problems. So let me first introduce the basics of Bayesian optimization. So in Bayesian optimization, we're interested in solving this black box optimization problem. The objective could be non-convex and multimodal. Our approach is modeling this objective function as a Gaussian process, and the Bayesian optimization strategy is to sequentially and adaptively sample points in hope to find the optimal solution. And based on these samples, we can construct the posterior distribution of L at unsampled locations. And based on this posterior distribution, we could define an acquisition function Q that measures the value of each point for our optimization purpose. And in each step, we maximize this acquisition function to decide which next subpoint to sample. For example, one common acquisition function is the expected improvement, which is defined as the expectation of improvement over current best solution. It's not surprising to find more and more applications of BO in control system. Let me list a few of them: PI tuning, LQR tuning, MPC tuning, set points or design parameters optimization. Meanwhile, in machine learning community, there are many different variants of BO that is developed. For example, safe BO, which has unknown safe set and reject even tiny violations, and generic constraint BO, which has unknown inequality constraints and agnostic to violation cost, and cost or budget aware BO, which has evaluation cost budgeted. For example, computation time budgeted, that does not consider explicit violation dependent cost. So a natural question is, how can we match different variants of BO to the rich applications in control? How can we handle violations? And in the inverse direction, the question is, can we extract a new setting from the control application to develop a new variant of BO? In this talk, I will introduce a new variant of BO, allowing more flexible and problem-specific treatment of violation for control application. So we will need to first introduce the concept of violation tolerance. We notice that in many applications, huge violation is for sure not tolerant, but some short-term and small violation is totally tolerable. For example, in the vapor compression system, we try to keep here the discharge temperature below a threshold. And there are three possible cases. In the first case, there is no violation at all, which is good. In the second case, there's a very huge violation, which is for sure intolerable for the system. And there is also a third case, where there is constraint violation, but the violation is small and only keeps for a short term. We observe that such small short-term violation is tolerable with very limited cost. And this motivates us to exploit such tolerable violation to benefit the tuning process. Now, let's formally give our problem definition. So we formulate our problem as a black box constraint optimization problem. Here, the objective is the closed loop cost of the system. For example, the steady state power in VCS. And the constants are the physical constants of the system. For example, steady state discharge temperature in vapor compression system. Both objective and constant are black boxes. Each round of sample with theta t returns the evaluations of L and G. We model L and G as sampled from independent Gaussian processes. Different from conventional Bayesian optimization approaches, we introduce the concept of violation cost, which is defined as a function C of the violated part of the constraint. This function C is user-defined and captures users' tolerance to different levels of violations. For example, we can set it to be infinitive positive, which reduces to the case of safe BO. We can also just set it to be 0, which reduces to the generic constant BO setting. And the user will also give some budgets, including sample budget capital T and violation cost budget B. Our goal is to sample a sequence of points to minimize the best feasible solutions objective that we find, subject to that the cumulative violation cost is upper bounded by B. Now, before I introduce our solution, let's first look at how generic constraint BO solve this problem. The idea is to maximize constraint expected improvement in each step. So constraint expected improvement is defined as the expectation of two terms. The first term is feasibility indicator. The second term is the improvement term. But the problem with this approach is that we still may sample point with intolerable violation cost with very significant probability. So in our violation-aware Bayesian optimization, it still maximizes this constant expected improvement objective. But as an addition, we introduce the violation-aware set. So this violation-aware set is parameterized by beta, which is a value between 0 and 1, and the remaining budget, the small value epsilon. So we solve this auxiliary constraint problem in each step and sample the optimizer of this auxiliary problem. So the idea is that we do constant BO as long as we do not use up a fraction of the remaining violation budget with high probability. So before I show you the application on a real system, let me first give you some result on a simple problem. So we sample functions from Gaussian process with Gaussian kernel and try to solve this minimization problem subject to that, we do not sample some points with positive F. We start from initial feasible point, and this is a typical result of CFBO. So we notice that CFBO fails to identify global optimal and is restricted inside a local region. So it has to pay the price of safety. For generic constant BO, this is typical result. It can identify global optimal, but unfortunately, it may also sample some points with very huge constraint violation, which could be dangerous to the real-world system. And this is a typical result of VABO. So it can simultaneously identify global optimal and manages violation well. We run our algorithms over 100 different instances, and we observe that in most instances, we do not use up the violation cost budget. Indeed, we can theoretically show that for any small dirt, if we set epsilon to be small enough, then our VABO satisfies that we do not use up the violation cost budget with very high probability. Now, we move to the real-world application that motivates this work. So the real-world application is a vapor compression system. Our goal is to tune multiple internal variables for optimal operation of this system. Note that some combinations of these variables may result in constant violations. And the mappings from internal variables to objective or constant is unmodeled. Our objective is to assign internal variables to minimize the power, with a constant that the discharge temperature is below a threshold. This constant prevents excessively high discharge temperature that can result in the breakdown of the refrigerant oils and increase wear and tear, and cause metal fatigue and compromise pressurized refrigerant pipes. In this scenario, small violations of short periods of time is acceptable. So our solution VABO takes observations of steady state power and discharge temperature from the system in each step. And based on the historical evaluations of power and discharge temperature, our VABO will sequentially and adaptively assign expansion valve position, indoor and outdoor fan speed variables to the system. And we use a Modelic-based simulator of a production-level vapor compression system with single-zone occupied building room. We compare our solution against the state-of-the-art safe Bayesian optimization and constant Bayesian optimization methods. We will use VABO X to denote the VABO with violation cost budget X. To demonstrate the result, I'm going to plot three figures. The left figure is the power. The middle is the discharge temperature. The right is the violation cost. So this is the result of CFBO. So you can see that it respects the constant all the time. This is the result of generic constant BO. You can see it converges much faster than CFBO. Unfortunately, samples some point with very huge discharge temperature and violates the constant because very huge cost. And this is our VABO solution. When we increase the budget, it converges faster. And compared to before optimization, our VABO reduces the power by about 9%. We observe that VABO incurs more violations than CFBO, but converges to more efficient power faster. And VABO evolved to be more conservative in later iterations, while CFBO still has large constant violations after 10 steps. And our VABO manages violation very well. In conclusion, I've told you about VABO, violation over Bayesian optimization, which automatically optimizes closed-loop performance despite unmodeled objective constants within admissible violation levels. We also provide a tractable solution for applications where short-term small magnitude constant violations are acceptable. We compare our VABO with safe BO and constant BO on a production-level simulation model of a vapor compression system and demonstrate superior optimization performance with safe exploration. In the future work, we're exploring more applications in energy systems. For example, building controller tuning. Thank you.